Welcome all. Our next speaker is Florence. He's a data generalist, open source developer, and an active Postgres contributor whose work spans database engineering. Today, Florence will show us what happens when a SQL meets Python, specifically how you can extend databases using Python without writing a single line of C. So, welcome, Florence.
Thank you for the intro. Didn't expect that. Well, thanks for being here. I realized we had a lot of British or almost British accents, so a Southern Eastern European one was missing from the menu. So here it is. I hope you don't get easily offended. I sometimes be a bit cynical or aphoristic, but don't take it personally. So if you are sensitive, now's the time to leave the room. So, as the intro said, I am a data journalist, which sounds a bit pretentious, I know, and very like data thinker or whatever. Long story short, I started working with Python as a data engineer like almost 10 years ago. So I was a very early pandas and all PyData data stack adopter, but then as my career moved forward, I became more realist and more cynical. I started doing more SQL and simplifying things on the stack. So now I'm PostgreSQL contributor. I do a lot of extensions as well. But during my career, I've done different job titles like this one, which again you were warned, right? Even those that come here. So I came to realize that a lot of things that we do on the data engineering lifecycle is all about trying to make up for the lack of ACID compliance. I won't discuss a bit in detail what ACID compliance means, but it's the important thing you get when you use a database instead of doing it by yourself. So atomicity simply starts that when you have a data system and you have multiple transactions like save, read, save, usually either one fails or all fail, right? So you don't have partial commits in your database. Consistency and isolation, you can get the idea there. And durability, if you restart the system, it works. If you see a lot of libraries that we now use in the PyData stack, it's about moving data around from point A to point B, right? So my whole premise is that we do infuse more complexity than we actually solve, and eventually we find ourselves doing some classes and actor and creator and all this gluing together, which basically what we're doing is creating a declarative layer on our data pipeline, right? So let's see what the procedural / relational mean. So that's programming 101 or CS 101 if you like. The first scenario says, okay, I have a for loop, I do some iteration of it, find the minimum and get a result, right? So that's what we say the procedural. We describe what the computation is and how we do it. The other approach is a relational approach that says I don't have multi-lines, I don't have for loops or if-else statements. Instead, I've expressed it in a query language or a declarative query language. I express it here and let the database do the computation for me to derive the algorithm and the execution of it. So from a programmer's perspective, a database is two things. Is one, an infinite memory emulator. You can have 1 GB of RAM and 10 TB of disk. And when you use a database, it pretends or imitates that you have like 10 TB of RAM. That's the whole premise of how it works. And the second thing is that it's also a compiler. So you have an SQL query, and then you express it in an almost physical or natural language, and then it derives an execution plan, and you get back a tabular result. So pandas became actually the cornerstone of the PyData stack because it allows you to do this, but in a declarative-like layer, but in a procedural form. But then you don't have any for loops here. So it almost looks like SQL, but it's not SQL, right? But you're still constrained by the main memory. You have to load the whole data frame in memory. So we pandas all the things. We ran into out-of-memory errors. We found ourselves in interactive programming hell. If you have used beyond the quick start application like a notebook, you probably have came across errors like, oh, I haven't run this cell, so good luck trying to import some logic from one notebook into the other, and so on. And you also get all the complexity about integrating like BI tools. BI tools have been speaking SQL for like almost 50 years now, right? Before even Python was an idea, right? So keep this in mind. So let's reinvent SQL. And whoever for the last 70 years has tried to reinvent SQL, they have found themselves trying to do it, and they always do it poorly, right? So they claim almost SQL compliance and so on. So my thesis is we should use SQL more. It's less complexity, less DevOps. It has built-in integration with BI tools, easier to learn if you try, and improves performance. This is the best way to improve performance in systems. Almost always the push-down optimization, which basically means instead of copying the data from the disk in memory, doing blah blah blah, just send the query to the database. I know this sounds like, and to some extent, I mean that there are a lot of job titles out there that should not exist. So again, don't be offended, but yeah, it is what it is. So SQL is standard query language. Whenever we get standard with programmers, we want extension as well. So yeah. So the extension mean about how to import in SQL. Has anyone used like an SQL database extension, or they know that they use it? Yeah. So there's a naming problem, marketing problem. When we hear about extensions, we think like, I don't know, Chrome extensions or anything, right? When it comes to database, extension can be very powerful. It could be like time series, can be whole domains. Like a real-time database can be an extension of a database, right? So are they very powerful? The whole companies can be backed by them. Like Citus is the most important case, like a distributed Postgres. You can have whole domains, PostGIS, libraries, and so on. From a developer's perspective, and a database extension is basically a binary, a dynamic, a shared object, like some bunch of bytes, which you load into a running process. So how do you and why do you extend SQL? You do that for two things: to get custom function and custom types, so they can use them in SQL queries, which is, if you think about this, sounds simple, but it's extremely, extremely powerful. So Postgres is the best database in the world. We should, yeah, don't laugh. This is not a cynical part, it's a realist part, right? So you keep laughing, but I mean it. You know, I say I mean it because, you know, there's a junior guy always who says, oh, dear senior, what is the best database in the world, right? And then you have, oh, yeah, there are pros and cons on everything and so on. No. We should be opinionated. Not being opinionated doesn't help. So you find like junior guys say, oh, we need a big query cluster to run our like 10 kilobytes sheets or whatever analysis, right? So it is extensible by design. Quick preview of some examples I have made. Just out of simplicity, what monstrosities or useful things you can do. This is PGPDF, a PDF type for Postgres. You use PyPDF, I think, right? So someone at least to import a PDF. I will give you 100 euros if you do it in less code than this one. You install the extension, you do select colon PDF, you get the text in the database, right? So you can do operations like this within your SQL, load the file into the memory, do concatenations, blah, 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 the whole shebang. There's HTTP, another extension, which allows you to do this thing that you should not do, but you can do if you want, right? But do it in production. Basically, you grab a random PDF from the internet, you shove it in your database. Good luck finding another job. Yeah, you use JQ, I guess, right? So I've some at least once. So this is another extension I have made that says, okay, I want JQ syntax in SQL. So here you have PDJQ. I have another one for SQLite, which is called LiteJQ. Innovative. And then that's another monstrosity. So if you use Redis at least once, right? This looks like Redis but in SQL, right? So shared memory, but in Postgres. But now let's get to the core of it. So extending Postgres with Python. So how does it look like? Ta-da! Yeah, yeah, that's well. So that's really good, actually. Yeah, I've done this presentation for the last every now and then for the last 2 or 3 years. I try the same prompt, and every new generation of LLM makes it much better, right? So that's the benchmark there, right? So how do you extend Postgres with Python? You can be mostly done with C, but not necessarily. Postgres is makefile based, the whole infrastructure of it, and you can use PL Python. This stands for procedural language Python. Like almost any database has a procedural infrastructure built into it. So let's take this example here. Suppose you have a string, right? And you want to emulate or recreate the join function, like you get a string, a list of strings, sorry, a separator and join them together, right? And you don't want to do it in SQL. How this works? You say I want to create or replace a function, right? This is in SQL level. Notice that here, the only pure Python part is this between the two dollar quote signs. So you go to the database and you say, okay, I will create a function, right? This is an SQL function, meaning it can be used from SQL, right? So you use this syntax here, you specify the arguments, the default arguments, and then you get some metadata into the optimizer, right? So whenever you go on and say select py string join, blah, 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 within the database will say, okay, I have this py string join into my catalog, right? It gets this and these arguments, so that's the parsing part, it does the compiler part, and whenever I want to actually execute it, I will go to and load this Python from a shared object, which is actually the CPython library, the dynamic library, right? I won't get into the details of that, but I want you just to know that it doesn't move any data out of the database into a running process. Instead, it gets the executable Python shared object, it pushes it to the database, and then you can have call the function from there. The important part is this metadata here, because databases are very, very smart. They have this thing called the optimizer, which has all the optimization and so on within the database. You have to let the optimizer know some metadata about the function, whether or not it is parallel safe, right? So whether or not it's not parallel safe, like it changes data on the fly or not. Whether or not it's immutable or not the function. So if you get this information to the optimizer, it can make many a very, very big difference for your to your pipeline, right? Let's see how we can use it. So you can use like py string join and separator and so on, the whole thing you could do, but you can imagine this in like complex SQL queries, right? Let's do another more complex example, which is moving average in Python, right? So you know what the moving average is. Again, here's a pure Python example. Again, the signal is the function. You say that this returns a float, which is actually a list of floats, but SQL doesn't have a list of sorts, it has an array, right? So internally, it will understand that basically a list in Python, which is implemented as an array list, I think, yes. It can be transpiled or converted or transformed as a type into a SQL array. And again, your metadata here. Notice that this is here is unsafe, the parallel part. And then you can do like the moving average of it, right? What's the alternative there? If you have lots of this data, what people usually do? Pandas, right? So if you have 10 terabytes in your data, in your table, or a few gigabytes or whatever, and you're constrained obviously by memory like 10 gigabytes or so, you have to load the data into a data frame just to have a moving average or a sum, cumulative sum or whatever, right? So again, here you push the computation to the database, you don't move any data around. Another example. So one of my favorite modules in Python is the iter tools, and more iter tools. If you don't know it, still it's very interesting. And then operators like this one, like zip. So basically, how do you do this in pure SQL, right? So people actually use, you tell you, okay, how can I zip whenever a BI person comes across this thing that says there's seemingly simple asks that BI people or marketing people ask that they're very complicated to do in SQL. So you get things like, okay, I have this report, and then a business person tells you, can you transpose this? You'll break your fingers trying to transpose this with your keyboard, right? It's very hard to do in SQL, right? So, but if something you have like iter tools in your tool belt, zip in this case, you can say that, okay, I'm going to create a function that's called bzip. It takes 2 arrays of text and returns a yield generator. I want you to notice that PL Python internally, you understand that a generator, it will translate itself into a table of text and text, right? Again, the alternative here is to load the data from disk, create a data frame, and push it back to the database, create a table on the so on. So this is how you use it. The examples, obviously, I guess you have used zip at least once. Another example I want to show, this is a contribution I did for PG19, the next one. Long story short is how to get like a base 64 URL encoding in core Postgres. But I wanted to have this because the way I implemented this is in typical C, you get like a vocabulary and so on, you translate each character into another character. That's fine, but there is another more weird way which you can do, which, long story short, I have created this function in C, which is base 64 URL encode, which behind the scenes it goes on. Does anyone use CPython from C? Has anyone read CPython from C? Like Python beyond the programming language, also a library, right? Hence the CPython. So what you can do is go into a C program, call me Postgres, and call another program called here Python, right? So you can do this thing here, blah blah blah, and go on and call the encode URL function from standard Python. You can do this for all sorts of things. Long story short, you can call NumPy, for example, from an extension. You can use I don't know, pretty much any Python or even CPython itself library from there. That's a bit tricky, right? The previous one. So this I showed. PL Python considerations, ergonomics can be a bit tricky. Visual environments are still a bit flaky, so you almost always have to use the system level binaries. You don't have version control, right? Because whenever for every new change you have to create or replace the function, but as long as your signature is fine, your pipeline is also fine. And this is called PL Python 3U for a reason. U stands for unsafe, so be extra cautious what you push into your database. That's with Postgres. Now SQLite and DuckDB, right? What's the difference between Postgres, the best database in the world, and SQLite, the most popular database in the world? Is that Postgres is a separate process. It's a client-server database. SQLite is, as we say, embedded database within a running process. So again, don't be offended, but 99% of the companies claim that they have big data, right? They can fit into running into a SQLite or DuckDB, right? Sorry, not sorry, right? So how do you extend SQLite with Python? Does everybody know that you can do this SQLite 3 import SQLite 3? So what not many people know is that if you have standard Python, you have a SQL database out of the box available for you, right? And it's probably the most underappreciated standard Python feature. STD, oh, that's not weird. Okay, PyString join in SQLite. This is much easier. This is 100% standard Python, no pip install, no VM, no SQL, no nothing. You just say import SQLite. You open a new connection. You can either do it in memory, right? Main memory, or you can specify a file on disk and you can create a database on the fly. And then you're going to say, okay, stop the execution there. I'm going to create a new Python function the way you know it, right? But when I open the connection with the database, I will say dear connection, create a function, which this is the name of the function I can call within my SQL queries. But instead, what we're going to do is you're going to call this Python function here, right? The number of arguments, some other metadata, and blah blah blah. So here you can do connection execute, blah blah blah, PyString join, you will stop the execution, go on and find where this is defined, and so on. Of course, here you can do even more fancy stuff. You can do, I don't know, import pandas within the function, or import a new library within the function, and you still have access to it within SQL. If you realize how powerful this can be, good for you. If you don't, bad for you, but you will eventually, right? And current fetch one, whatever. Yeah. So in DuckDB, DuckDB is DuckDB is like from CWI, right? So we are, I think Hannes or the other DuckDB guy was a keynote, I think, last year for PyData, I think. Yeah. Anyway, so DuckDB is SQLite, but for all up, call me analytics tasks, right? So optimized for analytics. The good thing is that you can open an existing SQLite database with DuckDB and it will just work out of the box. So this means that you have some similar functionality out of the box for creating functions as well. So again, you open a new connection, you have to do pip install here, of course. This is not standard Python. So blah blah blah, the same definition, create a new function. You have to specify some transformer types in the DuckDB case, but you can still use this again into your SQLite queries. Much more interesting scenario, custom aggregates. So aggregates, the most people usually with SQL do reporting. You start doing analytics the moment you start doing some min, max, or order by, right? This is where analytics start. So sum and average are the mostly used aggregates. Aggregates means that from a bunch of rows I get one single value, right? So let's create a correlation matrix. Correlation matrix says that whether or not column A, right, or column B are correlated using some algorithms, how much the score is it, right? So there are a bunch of Pearson and Spearman correlation that are the most probably useful ones, but they usually focus on they score 1 for only linearity, and for non-functional non-linear relations they score, they cannot detect such associations, right? So there are a bunch of 2 or 3 actually new correlation statistics that have come up in the last 15 or 20 years. Maximum risk coefficient is one, and the other one is the Xi correlation coefficient, right? So this is a PGXi core. Is that, long story short, you have a table of with 2 columns like this. You do a select Xi core on X and Y, and you'll get to a correlation score 0.5, right? This is an extension of mine. I have written this in C for Postgres, but I will show it how we can do it with pure Python, right? So in C I had to hand code it myself from the paper, but in the Python case I realized that SciPy also already has this coefficient, right? So I wanted to use this into my SQL queries. If I hadn't created the extension, or if you don't want to create like this, the way you do it is, okay, I want to use the Xi correlation coefficient, have point A, column A, and column B. You have to load it into memory, call SciPy, import SciPy, do the score, save it to the database, right? Why not do the other way around? You specify a new custom aggregate. This is standard Python again. So for an aggregate function, you have to set up the initiation, and then for the step part, which is whatever new value you get, what you do with it, and then a finalized part, a 3-step process how to compute an aggregate. We do this, basically we just call this SciPy function from within here, and then we have like 15 lines of code, is it? And then you can do things like that. You have your table already there, you just select the function you defined earlier. It goes on, loads the function in memory, does the computation, and you're done with it. And I think we're almost there. So now the presentation is over. So advice for Pythonistas. First one is yes, my favorite. The computer that got us to the moon had only 74 kilobytes of RAM. Let that sink in a bit, right? So you don't have big data again. So think about it whenever you ask for more resources. Aside from salary, you should always ask for higher salary, right? Learn SQL, advanced SQL, right? People, learn for select from where, group by, even using having SQL is considered advanced SQL nowadays, right? But this is outdated knowledge. In that, we had this since the 80s, so we're like 2025 now, right? Learn how DBs work, very rough terms, like what's the shared buffer, right? What's the disk, what's the optimizer, and so on. Before you move data, move queries and programs, the push down optimization I mentioned earlier. Move data only if necessary. If you're doing BI, learn about window functions, right? Who knows about window functions? Have you used it at least once? Who knows how window functions work internally? I got it. So you don't have to. It's extremely complex. Like even people who actually write the implementation of window functions for databases, it's difficult to express it in SQL terms, right? But because they're so difficult, there's so many questions Stack Overflow, there's so many answers Stack Overflow, and that's why LLMs are so good at answering questions about them, right? So if you know roughly how they work and why they exist, and you can frame your problem like this, then you can vibe code your day away, right? Be declarative. C is the end of Python of this, right? So be explicit rather than implicit, that is. Then be diligent with your imports. Don't pip install whatever you see out there, especially if you don't need it, right? And then it's more powerful than you'll accept. Okay, that's fine. I think that's it. That's me. Thank you for being here. Apologies if I insulted you. Sorry.
Thanks for the presentation. I had a question. We're using Databricks, and they now have this lake-based offering, which is basically also Postgres. Does all the stuff you showed about Postgres also hold for that version, or is it the same or different? Can you share something about that?
It's a complete. So I know the folks behind Lakebase, right? So Heikyo, the other guys, they are major Postgres computers. They are doing they're doing amazing stuff. Now how they mix, if it is indeed 100% compatible Postgres, it's okay. The great innovation about I remember from Lakebase and database is basically Neon, right? So from the acquisition, the important thing I could see from Neon is they could spin up like a new database in half a second, and then you can branch out. This is extremely powerful. And for the agentic process, you can just how it's called, like if else execution, if this happens, whatever. It's extremely powerful. Be diligent on what if they are 100% compatible with Postgres or not. But other than that, they are offering, yes, so sure. Yeah.
Thanks.
Yeah. So you mentioned that this is mainly a way to tackle the problem of not having to load everything into memory of your PC. How do you compare this against libraries that use a streaming engine like Polars to avoid that memory issue?
Do you need Polars? Do you need a streaming engine? Right? Do you need the real-time data or streaming data or whatever? If you do like vectorized execution or so on, my thesis is that let's not 90, like 80% of the problem, it boils down to DevOps costs, right? So with Polars, if you pip install or whatever, if you run into problems of it, even if you have some necessity of it, maybe you create more problems that you want to solve with the DevOps. If, however, you want to the streaming execution, the vectorized execution, or whatever makes a big difference for you, then go for it. But I don't think they compare 100% side to side. I think, for example, in my experience, most of the companies can get away with refreshing materialized views very often, and they don't really need vectorized or like streaming or whatever execution. But it's a bit simplistic, though. I know.
Okay, thank you.
Thank you.
We'll be meeting after a short break. There will be 15 minutes break, and the next talk will begin by 2:10.